Hey folks, I want to record some stuff for people that might be absent. We're going to look at a problem where we've got a function. It's called e to the point 4x. And there's a point on that function that's moving and it's connected kind of to this point that I'm dragging on the x-axis. So p is the point down on the x-axis that I'm controlling. And then this point up here has that same x value as p does. And then its y value is determined by this function, right? And so I'm getting this problem from our textbook. It's problem number 14. And it says, pretend like you have some point on the x. Well, you're dragging point B, which I think I could do on my program. Drag point B and then see what happens. No, because I connected it to my x value. Because they do say pretend like x is increasing at a constant rate. Right in here it says if you drag B in such a way that x increases at 2 units per second. So I just thought it'd be easier if I just kind of put this point down here and then connect, like that point's determined up here by wherever this x value is, okay? So let's just look at the problem in the textbook. It says, we're going to display the length of AB. It's kind of like this program we don't have access to anymore, or you don't, I do. And we're supposed to describe what happens to the length of AB, segment AB. And let's just look at it for a second, okay? So segment AB goes from the origin out to that special point on our e to the point 4x function, okay? And they're wanting us to determine if it's moving from left to right, what are the rates at which the length is changing at certain spots where, P is like at 5, I think, or P is at -1. What are the speeds at which that length is changing? All right. So it says, right in here, at what rate is the length of AB changing at the instant when x is -5? Oh, and x is 2. Okay. So what we do is we're going to follow this little technique. These are called related rate problems. And it's because the rate at which the length is changing is related to the rate at which the x value is moving along the x-axis. So write the given rates and rate that you're asked to find as derivatives. So it tells me that the x is increasing at 2 units per second. So I'm going to put down here 2, come on, 2 is equal to dx dt. So dx dt is equal to 2 units per second, okay? So the given rate, there's only one piece of given information, and that's that dx dt is changing at 2 units per second. The rate that we're asked to find, I'm going to write that down right now. The change in the length of the segment with respect to time. That's what we're supposed to find. It says, how fast is the length AB changing at the instant when x is -5? So at x equals -5 and at x equals 2, we're supposed to find dl dt. So I've taken care of that first bullet in our technique. Second thing is write an equation that relates the variables that appear in the given desired rates. So I've got an x and I've got an L. So I need a formula that will relate length to the x value that we saw on our program. So how is the program figuring these lengths out, that it's 16.2 or 7.15 or whatever it's doing, right? So it's just doing the distance formula between 2 points. So the nice thing is A is at the origin, 0, 0, and then B is at some x e to the 0.4x, okay? So that's how I figured out what the y value was for that point. So I'm going to use the distance formula, and I'm going to put down my 2 points are 0, 0, and x comma e to the 0.4x, right? So the distance formula works like this: x minus 0 quantity squared, or just x squared, right? I hope that's okay. I don't need to put the x minus 0 in there, I hope. And then plus, we're going to go e to the 0.4x minus 0. So that's e to the 0.4x. And okay, so now I've got a formula that relates x and L. So this is number 14. So it's maybe a trickier one of the related rate problems. So check mark, taking care of that. Differentiate implicitly with respect to time. that means we're going to get dl dt. Hey, look at that. That's what we're looking for. We're looking for dl dt. And so we're implicitly differentiating. Now, this square root sign is the same thing as the half power, right? So I've got something to the 1/2 power. So my first layer, if I'm going to number the layers, I'm going to put that first layer right in here, and it's going to be move the 1/2 down out front, rewrite everything inside unchanged, and reduce the power by 1, right? So what was on the inside here? It was x squared plus e and 0.4 times 2. When you raise a power to a power, you multiply them together, right? So 0.8x. So let me copy that down here. X squared plus e to the 0.8x. But we have that layer also. So let's put another number here, 2, my layer number 2. So this was layer number 1 right here in my derivative. Okay, here comes layer number 2. All right, that's going to end up sitting right there. So what do? I go 2 times x, so 2 times x to the first power. Now I got to keep in mind my goal is to differentiate with respect to time. So is x is it in terms of time? Do we know what x is in terms of time? No, we don't. So I've got really like a new layer there. Like if I don't know, choose yellow here, I've got a layer, let's call it layer 3. It didn't change to yellow, probably because I didn't hit commit or whatever. So I've got a layer right there. So I'm going to put down the derivative of the inside function with respect to time. So it's going to be dx dt. That's implicit differentiation going on right there. Then I'm going to go plus. Okay, so I'm still at layer 2 here. And I stepped in and I did kind of like layer 3 when I took the derivative of the x right there. So then I got e to the 0.8x. Then the inner function here is 0.8x. So I'm going to put down times 0.8 dx dt. Dx dt. Because I got to take the derivative of the x value, and I'm going to put, dx dt, because I don't know what x is in terms of time. So let's see here. I've done the chain rule. I think I took care of every little part. I took care of my implicit differentiation. So right here, differentiate implicitly with respect to time. So check mark. Then it says, then solve for the desired rate. Now, sometimes it's best at this point to plug in your known pieces of information, and sometimes your functions solve for your desired rate, which in this case it is. So just putting in the 2 for my dx dt and putting the -5 in for my x's will tell me what the final answer is. But sometimes when it says solve for the desired rate, like sometimes we're looking for dx dt, so moving everything away from the dx dt is a good thing to do. But for right now, I think I'm ready to go. Now this can be written, a couple different ways. Like I could move this to the denominator and all that kind of stuff. And we're plugging 2 in for dx dt, right? So 2 is going right there and 2 is going right here. Why is that? Because it says dx dt is 2. Okay, they're going to tell us that kind of information. dx dt is 2. So we're replacing those with 2. Now, that 2 could factor out and cancel with the 1/2, right? That's kind of still part of this line right here where it says solve for the desired rate. So maybe it's best if I do something like that right now. 2x, I'm going to put the 2x e to the 0.8x. Well, I've got a 0.8 in front of that. 0.8 e to the 0.8x. And then all of that is over x squared plus e to the 0.8x, and that's all square root, right? Because the 1/2 power, right? That's why I moved it to the denominator. And then this 1/2 canceled with these 2's over here that I could distribute out to the front. Man, I hope that's clear. Now, technically, I'm done with this whole part, solve for my desired rate. I've simplified a little bit. All right, what's coming next? We're going to plug in our 2 different numbers at x equals -5. At x equals -5, dl dt is equal to 2 times -5 plus 0.8 e to the 0.8 times -5, right? And then that's all over the square root of -5 squared plus e to the 0.8 times -5, right? This is time for Desmos. We're plugging all that into Desmos, trying to get a decimal approximation, or we're going to simplify it as much as we can. But we're doing this part right here where it says x equals -5 and x equals 2. That's the related rates part of this equation, of this problem. Now, the rest of this, at what value of x does the length of AB stop decreasing and start increasing? So let's look at that on Geo Sketchpad here. If I just focus on the length of AB, right? So we're over here right now. It's 4, 3, 2, 1 point something, 1.1, 0.9, 1. Oh, so it's right in here where it goes from 0.9 something back up to 1. So it was like 1.9, then it's back up to 1 and increase. So right in here is where the minimum value is. Right? How would we determine that where it says at what value of x does the length of AB stop decreasing and start increasing? Explain how you arrived at your answer. Well, I'm just doing that using Geo Sketchpad. But I want you to think about, is there a way to use some of these ideas here to figure out what that point is exactly? Okay. Like where is dl dt going from negative to positive, right? Because at -5, you're going to get a negative answer here. At 2, you're going to get a positive answer, because if I'm over here at -5, oops, shoot, I'm moving the wrong point. Let me try that again. So my point's so close to the origin. Okay, here we go. So if I come over here to -5, notice that the value of AB is getting smaller. So that means dl dt is negative. But if I'm over here at +2, AB is getting bigger, so dl dt is positive. So where does the derivative go from negative to positive? That's where our minimum value is going to be. All right. I want you to try that.